oscillating between three different types or flavors: electron neutrinos, muon neutrinos, tau neutrinos. They were shape-shifting, and Davis's detector could only see electron neutrinos. The others passed right through without registering. The mystery was solved. Crisis averted, except it revealed something even more unsettling. We were fundamentally wrong about how neutrinos work. Neutrino oscillation meant neutrinos had mass. Tiny, almost negligible mass, but mass nonetheless. And that violated the standard model of particle physics, the framework that explains how the universe works at its most fundamental level. If we were wrong about that, what else are we wrong about? What's really happening in that unreachable core? We have theories, models, simulations run on supercomputers. But we've never been there. We never will be there. The core is forever beyond our reach, hidden behind 432,000 miles of plasma so hot and dense that it would vaporize any probe, any instrument, any material we could possibly send. And that's assuming the core is stable, which it might not be. Some models suggest the core undergoes periodic instabilities, brief moments where fusion rates spike or drop dramatically. These fluctuations wouldn't be catastrophic. The sun has enormous thermal inertia. Changes in the core take millennia to propagate to the surface. But they would eventually reach the surface, causing the sun to brighten or dim over centuries or millennia. Could this explain historical climate variations? The Little Ice Age from 1300 to 1850, when temperatures dropped and rivers froze? The medieval warm period from 950 to 1250, when Vikings farmed Greenland? We don't know. The data doesn't go back far enough. We only have detailed solar observations going back a few centuries. Before that, it's guesswork based on sunspot records kept by Chinese and Korean astronomers, on isotope ratios in tree rings and ice cores. But the possibility haunts solar scientists. The sun might not be the steady, reliable star we think it is. It might go through phases, angry periods, quiet periods. We might just be living in a calm moment, mistaking temporary stability for permanent safety. And there's no way to know until it changes, until the core shifts, until fusion rates jump, until the surface brightens. And by then, it's too late to do anything but watch. The maximum damage the sun can inflict on Earth is not theoretical. It's not speculation. It has happened before, in living memory, recorded in telegraph logs and newspaper accounts. September 1st, 1859. The Carrington Event, the largest solar storm in recorded history. British astronomer Richard Carrington was in his private observatory in Red Hill, Surrey, doing what he did every clear day, observing and sketching sunspots. The year 1859 was near solar maximum, the peak of the sun's 11-year activity cycle, and sunspots were abundant. Carrington was tracking a particularly large group when, at 11:18 a.m., he witnessed something no human had ever seen before. Two brilliant white lights appeared in the sunspot group. They brightened rapidly, becoming so intense they were visible against the sun's surface, even through his telescope's filters. A white light solar flare, the first ever observed. Carrington watched for 5 minutes before the lights faded. He immediately rushed to find someone else to verify what he'd seen. But by the time he returned, the flare was over. He made careful notes, sketched the positions, and recorded the time. He had no idea what he'd just witnessed. No idea that in 17 hours the world would change. At 1 a.m. on September 2nd, the first auroras appeared. Not in the Arctic Circle where they belonged, but everywhere. Across Europe, across North America, South America, Asia, as far south as the Caribbean, Hawaii, Colombia. The northern lights were so bright that people in the Rocky Mountains woke up at 1 a.m. thinking it was dawn and started making breakfast. Gold miners in the Colorado Rockies got up and began preparing for the day's work before realizing it was still the middle of the night. In the northeastern United States, people could read newspapers by aurora light at midnight. But the auroras weren't just beautiful. They were accompanied by something more sinister. Telegraph systems across Europe and North America went haywire. Operators received electric shocks from their equipment. Some were knocked unconscious. Telegraph paper spontaneously caught fire as phantom currents surged through the lines. In Norway, telegraph equipment was destroyed entirely. In the United States, messages were sent between Boston and Portland with the batteries disconnected. The geomagnetic currents induced in the telegraph lines by the magnetic storm were strong enough to power the system by themselves. What had happened? The white light flare Carrington observed was the visible signature of a massive magnetic explosion on the sun's surface. Energy equivalent to 10 billion atomic bombs was released in minutes. Most of it was in the form of a coronal mass ejection, a billion-ton cloud of plasma traveling at over 4 million miles per hour. It crossed the 93 million-mile distance to Earth in 17 hours. Normal CME transit time is 3 to 4 days. This one was moving at unprecedented speed, driven by magnetic forces we still don't fully understand. When the plasma cloud hit Earth's magnetosphere, it compressed our magnetic field like a spring. The magnetosphere, which normally extends 40,000 miles into space on the sun-facing side, was crushed to a fraction of that. Particles poured into the upper atmosphere, ionizing air molecules, creating the auroras, but they also created something else, rapidly fluctuating magnetic fields. And fluctuating magnetic fields induce electrical currents in any conductor. Telegraph wires, railroad tracks, pipelines, anything metal and long. But 1859 was a different world, a world of telegraphs and gas lamps, a world where electricity was a novelty, not a necessity. The telegraph system was the most advanced electrical technology of the era, and it was primitive by modern standards. A few wires strung between cities, simple circuits. If the Carrington event happened today, the damage would be catastrophic beyond comprehension. Every satellite in orbit would be fried. The Van Allen radiation belts, which normally protect satellites from energetic particles, would be overwhelmed. Solar panels would degrade. Electronics would be destroyed by radiation and induced currents. GPS satellites, communication satellites, weather satellites, military satellites, all gone in hours. GPS would be dead. And GPS isn't just for navigation anymore. It's the backbone of modern infrastructure. Cell phone towers use GPS for time synchronization. Power grids use it. Financial systems use it for timestamp verification. Without GPS, ATMs stop working. Credit card transactions fail. The stock market crashes. And that's just the beginning. Communication networks would be dead. No cell phones, no internet, no satellite TV. The only communications would be line-of-sight radio, and even that would be disrupted by ionospheric disturbances. Weather forecasting would be dead. No satellite imagery means no hurricane tracking, no tornado warnings, no advance notice of severe weather. But the real catastrophe would be the power grid. The electrical grid is a massive conductor, thousands of miles of high-voltage transmission lines connecting power plants to cities. During a geomagnetic storm, these lines act like antennas, picking up the fluctuating magnetic fields and converting them into electrical currents. Geomagnetically induced currents, GICS. During the Carrington event, telegraph lines experienced GICS strong enough to shock operators and ignite paper. Modern power lines would experience currents hundreds or thousands of times stronger. These currents would flow into transformers, the massive devices that step voltage up and down for long-distance transmission and local distribution. Transformers are not designed to handle direct current. They're designed for alternating current at precise frequencies, 50 or 60 hertz depending on the country. When DC current flows through a transformer, it saturates the magnetic core, causing it to overheat. The insulation breaks down. The transformer literally melts from the inside. And here's the nightmare scenario. We don't manufacture enough replacement transformers. They're custom-built, enormous, some weigh hundreds of tons. They take years to build and require specialized facilities. Most power companies keep few spares. A Carrington-level event hitting today would destroy hundreds, possibly thousands of transformers simultaneously across entire continents. Blackouts would spread in cascading waves. As transformers fail, load shifts to other parts of the grid, overloading them, causing them to fail in turn. Within hours, entire countries would be dark, and it would take years, possibly decades, to rebuild. Without electricity, nothing works. Hospitals would lose power. Backup generators would run for days or weeks until fuel ran out. Then people on life support would die. Water treatment plants would fail. No electricity means no pumps. Reservoirs would drain. Tap water would stop flowing. Within days, water in major cities would be undrinkable or unavailable. Sewage systems would back up. Supply chains would disintegrate. No electricity means no refrigeration. Food spoils. Grocery stores run out of stock in 3 days under normal conditions. In a crisis, it would be hours. Gas stations couldn't pump fuel. Even if fuel was available, the pumps require electricity. Transportation would grind to a halt. And remember, no GPS means no navigation for trucks, ships, planes. Ports would close. Airports would close. The global economy would collapse. Millions would die, not from the storm itself, but from the collapse of modern civilization in its aftermath. Starvation, disease, violence as societies break down. And the Carrington Event wasn't even the worst-case scenario. In 2012, a solar storm even stronger than Carrington's erupted from the sun's surface. The coronal mass ejection was massive, fast, and aimed directly at where Earth had been 9 days earlier. If it had hit, NASA estimated the economic damage at over $2 trillion in the first year alone. That's a conservative estimate. Some researchers put the damage at 10 trillion or more. 9 days. The difference between normalcy and apocalypse was the Earth's position in its orbit, where we happened to be as we circled the sun. We got lucky, pure chance. The storm missed us by a cosmic whisker. Next time, we might not be so fortunate. Solar physicists estimate there's a 12% chance of a Carrington-level event hitting Earth in the next decade. 12%. Would you fly on an airplane with a 12% chance of crashing? Would you live in a house with a 12% chance of collapsing? Would you eat food with a 12% chance of being poisoned? Yet here we are, utterly dependent on technology with no meaningful protection against the sun's wrath, accepting a 12% chance of civilization-ending catastrophe as background noise. Some nations are taking precautions. The United States has identified critical transformers and is slowly hardening them against GICs. Slowly, glacially. Budgets are limited. Politics interfere. Most estimates suggest full grid protection would take 20 to 30 years at current funding levels. Other countries are doing even less. The United Kingdom has conducted studies. China has built some shielding into new infrastructure. But globally, we're nowhere near ready. And we're running out of time. Solar Cycle 25 is currently in its rising phase, heading towards solar maximum expected around 2025. The sun is waking up, activity is increasing, and we're still arguing about budgets. But the sun can do worse than electromagnetic storms, much worse. If the sun wanted to kill us directly, if it wanted to end not just our technology, but our species, it wouldn't use flares or CMEs. It would use something we have no defense against, something we've only recently discovered is even possible, a micronova. In 1054 AD, Chinese astronomers recorded a guest star that appeared in the constellation Taurus. It was visible in daylight for 23 days, brighter than Venus at night. We now know it was a supernova, the death of a massive star. The remnant is the Crab Nebula, still expanding today, still glowing with the fury of that ancient explosion. But our sun is too small to go supernova. It doesn't have enough mass. Stars need to be at least 8 times the sun's mass to explode as supernova. Instead, in about 5 billion years, the sun will swell into a red giant as it exhausts its hydrogen fuel and begins fusing helium. It will expand, engulfing Mercury and Venus. Earth might survive on the outer edge of the red giant's atmosphere, or it might be consumed as well. Models aren't certain. Eventually, the sun will shed its outer layers in a planetary nebula and collapse into a white dwarf, a Earth-sized ember slowly cooling over trillions of years. That's the standard model, the safe, predictable narrative we tell ourselves. Our sun will die quietly, gradually, giving future life forms billions of years of warning. Except there's growing evidence that some stars, including sun-like stars, can undergo sudden, catastrophic outbursts long before they reach red giant phase. These are called micronovas or stellar superflares, events thousands of times more powerful than anything we've observed from our sun. In 2022, researchers analyzing data from the Kepler Space Telescope which monitored the brightness of over 150,000 stars for 4 years, found something disturbing. They identified dozens of sun-like stars that had experienced superflares, sudden brightenings where the star's energy output spiked by factors of hundreds or thousands. One star brightened by a factor of 2,000 in minutes before returning to normal over days. The energy released in these events is almost incomprehensible. A typical solar flare releases about 10 to the 32nd power ergs of energy. A superflare releases 10 to the 36 power ergs or more. That's 10,000 times more energetic. Enough energy to vaporize planets. When the researchers calculated the frequency of these events, they found that approximately 1 in 10 sun-like stars has experienced a superflare in the past century. 1 in 10. The energy released in such an event hitting Earth would strip away the atmosphere in hours. The radiation would ionize the air. Molecular bonds would break. Nitrogen and oxygen would be blasted into space by the solar wind. Oceans would boil. The surface temperature would spike to hundreds of degrees as the thermal radiation scorched the planet. Nothing would survive. Not in bunkers, not underground. The whole biosphere would be sterilized. Could our sun do this? The conventional answer is no. Our sun is too stable, too calm, too middle-aged and well-behaved. It's a G-type main sequence star, the most common type of star in the galaxy. Boring, reliable, safe. But the Kepler data suggests otherwise. It suggests that superflares might be more common than we thought, that the sun's apparent stability might be an illusion, a temporary calm in a much longer cycle of violence we haven't observed because we haven't been watching long enough. We've only been studying the sun closely for a few hundred years, a blink of an eye in cosmic time, a fraction of a percent of the sun's 4.6 billion year lifetime. What if superflares happen every 10,000 years? Every 100,000? We wouldn't know. We have no records going back that far. Human civilization is only about 10,000 years old. Writing is 5,000 years old. Detailed astronomical records are a few centuries old at best. All we have are geological hints, isotope anomalies in ice cores, and tree rings that suggest something happened. Something violent, something from the sky. In 774 AD, carbon-14 levels in tree rings spiked dramatically, indicating a massive influx of cosmic rays into Earth's atmosphere. Something stripped away the upper atmosphere's protective layers for a brief period. We don't know what, a supernova, a gamma ray burst from a distant star, or something closer? Something from our own sun? There's another event in 993 AD showing similar isotope spikes, and possibly others buried in the geological record, waiting to be found. What if these were solar superflares, subcatastrophic events, strong enough to damage the atmosphere, but not strong enough to sterilize the surface? Warning shots. If the sun can do this, if it has done this in historical times, what's to stop it from doing worse? The answer is nothing. We have no control, no influence. The sun does what it does, and we're just here, watching, hoping it stays calm. Which brings us to the final question. The question that haunts every solar physicist, every space weather researcher, every astronaut who has looked at the sun from orbit and felt its power. Why doesn't NASA reach the sun? Why don't we send a probe directly into the solar surface, into the corona, even approaching the photosphere, to answer these questions definitively? Why don't we go there and see what's really happening? The answer is both technical and existential, rooted in the limits of material science and the darker limits of human courage. Technically, it's impossible, or nearly impossible. The Parker Solar Probe, launched in 2018, is the closest we've ever come. It's humanity's fastest and most heat-resistant spacecraft ever built. The mission is ambitious, audacious. Over 7 years and 24 orbits, Parker will gradually spiral inward, using Venus gravity assists to shed orbital energy, falling closer and closer to the sun. By 2025, it will make its closest approaches, passing within 3.83 million miles of the sun's surface, skimming through the corona at speeds exceeding 430,000 miles per hour. That's fast enough to fly from New York to Tokyo in less than a minute. fast enough that even the vacuum of space offers measurable resistance. To survive, Parker carries a heat shield made of carbon composite foam, 4.5 inches thick. The shield is faced with a white ceramic coating designed to reflect as much heat as possible. Behind that shield, instruments huddle in relative safety, while the shield's sun-facing surface endures temperatures of 2,500 degrees Fahrenheit. Hot enough to melt steel, hot enough to vaporize most materials. But the instruments behind the shield stay at a relatively comfortable 85 degrees Fahrenheit, cooled by circulating water and the vacuum of space acting as insulation. And that's still nearly 4 million miles away from the surface. The actual surface of the sun, the photosphere, sits at 10,000 degrees Fahrenheit. No material can withstand that. No ceramic, no carbon composite, nothing. At those temperatures, chemical bonds break down. Materials don't melt. They sublimate directly from solid to gas. And the photosphere isn't even the hottest part. The corona, the sun's outer atmosphere visible during solar eclipses, paradoxically reaches temperatures of millions of degrees. We don't even fully understand why the corona is hotter than the surface beneath it, violating basic thermodynamics. Heat should flow from hot to cold, not the reverse. Something is pumping energy into the corona, heating it to temperatures that shouldn't be possible. We think it's magnetic reconnection, the same process that drives solar flares, but the details are murky. Any probe attempting to touch the sun would vaporize in seconds. The materials don't exist. We can't build them. We can't even imagine what they would be made of. The physics might not even allow it. There are theoretical limits to material strength, to heat resistance, based on the electromagnetic forces holding atoms together. The sun exceeds those limits. It tears atoms apart. It exists in a regime where solid matter cannot exist in any form we understand. So we stay back. 4 million miles. Close enough to learn something. Far enough to survive. But there's a deeper reason, an unspoken reason that scientists rarely acknowledge in public but admit to privately, over drinks at conferences, in late-night conversations, when the day's presentations are done, and the guard comes down. We don't go to the sun because we're afraid of what we might find. Or more accurately, we're afraid of confirming what we already suspect, that the sun is not stable, that it's not predictable, that it's a ticking time bomb we happen to orbit, and there's nothing we can do about it. Going closer, gathering more data, building better models, refining our simulations, it all leads to the same conclusion. We are helpless, utterly, completely helpless. If the sun decides to kill us, we die. No amount of technology will save us. No bunker goes deep enough. Even kilometers underground, the radiation would penetrate. The heat would seep down. The atmosphere would burn away above us. Eventually, the underground shelters would become tombs. No spaceship flies far enough. Where would we go? Mars. Mars would be sterilized too. The outer solar system? We don't have the technology to evacuate even a fraction of humanity. We can barely get a dozen people to the International Space Station. Moving billions to the moons of Jupiter is fantasy. We like to think we've conquered nature, that science and engineering have given us control over our environment. We've eliminated smallpox. We've split the atom. We've walked on the moon. We've sequenced the human genome. We've built machines that can think, that can learn, that can create art. We've bent the world to our will. But the sun reminds us of the truth. We're passengers on a rock, circling a fusion reactor, hoping it doesn't malfunction. That's not a comforting narrative. It doesn't fit the story of human progress we tell ourselves. It doesn't fit the idea that we're masters of the universe, that nothing can stop us, that every problem has a solution if we're just clever enough. So we don't talk about it. We take solar measurements, we update our models, we publish papers on coronal mass ejections and helioseismology and solar wind dynamics. We build better space weather forecasting tools. We issue alerts when a big flare erupts, and we pretend everything is fine. We tell ourselves the sun is stable, that we understand it, that the risks are manageable. We lie because the truth is unbearable. The truth is we're fragile. One bad day from the sun and civilization ends. One super flare and the species ends. And there's nothing we can do but watch and hope. Every morning the sun rises. It floods the sky with light, warming the earth, sustaining life, driving the cycles of weather and seasons that make this planet habitable. We've built entire civilizations around the assumption that this will continue forever. Religions worship it as a god, recognizing its power if not understanding its nature. Cultures celebrate it with festivals and rituals. Scientists study it with ever more sophisticated instruments. But none of us truly understand it. We don't know what it says, what song it sings as it tears itself apart and rebuilds every second in an endless cycle of fusion and convection. We don't know what lurks in its core, what reactions are happening in that unreachable inferno where matter ceases to behave by the rules we know. We don't know the maximum damage it can do, not really because we've never seen it truly angry. The Carrington Event was bad. The 2012 near miss would have been worse. But what if those weren't the worst? What if the sun is capable of something we haven't imagined? What if buried in the geological record are extinction events we've attributed to asteroids or volcanoes, when the real culprit was above us all along, 93 million miles away, close enough to burn us, and we don't go there. We don't reach it. We don't send probes into the photosphere or plunge instruments into the core. We don't because we can't, technically, but also because some questions are better left unanswered. Because if we confirm that the sun is unstable, that superflares are inevitable, that our stable period is temporary and the clock is ticking, what would we do with that information? Panic? Despair? Build underground cities and hope for the best? Or would we just continue living, continue building, continue hoping because that's all we can do? The sun is 93 million miles away, close enough to give us life. The Goldilocks distance. Not so close that we boil like Venus, not so far that we freeze like Mars. Just right, but also far enough that we can pretend it's safe. Far enough that we can't see the details without telescopes, can't hear the screaming without instruments, can't feel the fury without satellites to measure the radiation and particle flux. Distance gives us the illusion of safety, the illusion of control. We look up at a bright disk in the sky and see beauty, warmth, hope. We don't see a million-mile-wide ball of plasma held together by gravity, tearing itself apart with fusion every second, wrapped in magnetic fields that snap and reconfigure in explosions that dwarf all of human history. But it's not safe. It never was. The sun is a monster, barely contained by its own gravity, and we orbit it every 365 days, dancing around it in an ellipse, hoping it doesn't notice us, hoping it doesn't wake up. Because if it does, if it has a bad day, if the magnetic fields in its core shift just right and a superflare erupts, we won't even have time to realize what's happening. The radiation travels at the speed of light. We'd see the flash and die 8 minutes later. No warning, no time to say goodbye. Just a brightening of the sun in the sky, and then nothing. This is the secret they don't teach in school. This is what the textbooks don't emphasize. Yes, the sun is necessary for life. Yes, it's been stable for billions of years. Yes, it will continue to shine for billions more before it runs out of fuel. All of that is true, but it's also true that we're living on the edge of a knife, one solar tantrum away from extinction, and we have no plan B, no backup, no escape route. We're here on this rock, betting our species' survival on the sun's good behavior. And so far, we've been lucky. But luck runs out. It always does. The only question is when.